C'est... Bon, me fiche pour rien, hein, ça se trouve.
C'est pas que tu parce que c'est bon.
Ouais.
Donc voilà, ça fait du fume. Ça marche?
Ouais.
Et t'as réussi.
Là, faut pas parler parce qu'on va le micro, il est là.
Ouais, c'est ça.
Morning, everybody, ladies and gentlemen, dear colleagues. On behalf of the Scientific Committee of the conference, I have the great honor and pleasure of welcoming you warmly here in Lyon for the opening of Equa Diif 2015. As most of you probably know, Equa Diif in Lyon is not an isolated event. It is part of a series of European conferences which started as early as 1970 in Marseille, France, under the initiative of Professor Theodore Vogel. The meeting in Marseille was relatively small, about 40 participants. It was in fact a satellite conference of the International Congress of Mathematicians, which was held in Nice in September 1970. In Marseille, it was decided that the field of differential equations, including partial differential equations and functional equations, was important enough so that a regular series of conferences be devoted to it. So 3 years later, another much larger meeting was organized in Brussels and Louvain-la-Neuve, Belgium, another French-speaking country. And this probably explains why that name of Equa Diif was definitively adopted there for the conference. Equa Diif is a very common nickname in French for differential differential equations, but it doesn't mean match in many other languages. So subsequently, the Equa Diif conference visited Italy, Florence, and then Germany, Würzburg, Greece, Xanthi, Spain, Barcelona, and Portugal, Lisbon. In 1999, the conference was back in Germany for a very large meeting in Berlin, and in 2003, back in Belgium for a conference in Hasselt. The last editions of Equa Diif were held in Vienna, Loughborough in the UK, and finally now in Lyon. Quite remarkably, there is another series of conferences on the same field, under the same name, which an even longer tradition. It started in Prague in 1962, and for me it's still a mystery why Professor Kurzweil and Babushka chose to use that name of Equa Diif, which apparently has no special meaning in Czech. It also seems that people in Marseille in 1970 were not even aware of the conferences that were organized in Czechoslovakia, so that both series of conferences were completely independent, at least at the beginning. In fact, there is a big difference between Eastern and Western Equa Diif conferences. As you can see from this transparency, the Western series is a typical example of a chaotic and non-predictable dynamics. And it jumps from one country to the other, and nobody can predict what the future will be. In contrast, the Eastern series is a perfect example of a periodic orbit, because the conference is organized in rotation among the same three cities, Prague, Bratislava, and Brno. As you know, predicting the future of a stable periodic orbit is not especially difficult, so I have the pleasure to announce that the next Equa Diif conference after Lyon will be held in Bratislava in summer 2017. All Equa Diif conferences were organized in Europe, but they have a worldwide audience. The present edition in Lyon has attracted more than 550 participants coming from 47 countries, which makes it the largest edition of all Equa Diif conferences after, of course, the unbeatable 1999 edition in Berlin. Among all these participants, the largest contingent is from France, 129 persons, including, of course, local people in Lyon. Then we have as many as 70 persons from the United States, 45 from Germany, 42 from Japan, 38 from Italy, and 35 from the UK. And there are many other countries that I cannot see here. To conclude this very brief introduction, I would like to mention and to thank a few of the many people who contributed to the organization of the Equa Diif conference in Lyon. I will start with people from the scientific committee who selected all the plenary and invited speakers, as well as most of the mini symposia organizers. Of course, most of the actual work was done by the organizing committee led by Sylvie Benzoni and myself, which includes also 4 younger colleagues from Lyon, Morgan Bergo, Thomas Lepout, Miguel Rodriguez, and Julien Bobel, who helped us with many important and time-consuming aspects of the scientific organization. As for the practical organization, I mean rooms, foods, registration, social program, conferences, bags, and so on, this is the task of Cellule Congrès de l'Université Claude Bernard Lyon 1, and I would like to thank especially Solange Perel and Nadège Botia for all their work. And finally, we would like to mention that a good part of the scientific organization has been done, in fact, by the mini symposia organizers, 56 people, which are listed here. They contacted and invited most of the speakers of the conference, and therefore made a crucial contribution to the scientific organization. Thanks to all people who participated to organization. Thanks to all participants for coming. We wish you a very pleasant and stimulating week here in Lyon.
Good morning, everybody. So I'm Sylvie Bensoni. I'm very pleased and very honored to welcome you here in my university, on this campus, which is usually very green and fresh and trees. And it's nicely located. I'm going to give you some practical details also. It's nicely located next to the Rhone River and the Parc de la Telle, which I encourage you to visit. These ancient trees and nicely renovated zoo. This campus has quite a large math department. About 1,200 students are in the math department. And this math department is itself part of a research lab called Institut Camille Jordan. You will see the logo afterwards. And before showing you the buildings with the conference rooms, I can give you some piece of advice. If you want to visit a little bit our lab or visit some nice library with hopefully a little bit of fresh air, in particular in the basement, you can go on this. Can you see the glass here? This building called Braconnier is where we have the math department and the math library. The books are in the basement. It's a little bit fresh. And you can also visit, as an alternative, the main library, which is, if I'm not confused, okay, here under this arrow, you can't miss it because it's basically in between here and the tram stop. And if I'm not wrong, there is some air conditioning there. I'm not sure. Okay, so about the conference rooms. As you know very well because you are here, the registration desk is in this Astre building here, and you can come here by the tram, and the closest stop is here, called Gaston Berger. And then you have two tram lines to go to the city center, T1 and T4. So if we zoom a little bit, we see a little bit better the tram stop, the Astre building, the plenary lectures, and the registration desk. And about the parallel sessions, they will take place in this Themis building and in this déambulatoire building. So Themis is very easy to find, it's just across the street from here. There is an elevator to go upstairs to the two rooms which are not called amphi. And in this déambulatoire building, you have also 5 amphi. And it is where we will be all there tomorrow morning and also on Wednesday morning because we have the invited lectures in amphi 4 and 5. And also there will be some small book displays and poster sessions, as you will see on the overview here. Okay, you should know this table already. There are some colors which are hardly seen here. It's an updated version of it because, as you know, I emailed you, and it's written on the website. We had a cancellation, and Pierre Raphael has accepted to talk on Friday. What else? Today, the important thing is to know is that if you want to be on the picture, you have to be at the Rhone Prefecture or Departmental Council at 7:30. It is where the picture will be taken and there will be a welcome party there. And on Friday afternoon, there is some free time. You can spend it here working or going to some tours which have been proposed to you. And the social dinner will be at 8 p.m. on Wednesday, but it's if you have booked it, otherwise it won't be possible, I'm afraid. About last minute updates. So these color tables, I will not be able to update them all, and I will just update the website here if there are any changes. So you can go to these tabs, the main speakers, if unfortunately we will have some change there, or the mini symposium tab, or the contributing talks tab. And these, if there are any changes here, they will be listed in the news tab. Okay, so please, if you are connected, check this, and I will also try to make this appear on the registration desk. There is a copy of this huge poster with the whole program. So just a few details about this social program. Again, it's at 7:30 tonight, the welcome party. The tour will be starting at 2:30 on Wednesday. From here, there are, and what I didn't mention is that there are some young people with red t-shirts that you can follow. In particular, this is one thing I forgot, very important, food, lunch. Lunch is here at the Post restaurant called Jussieu. And if I understood well, some young people with red t-shirts will take you there. It's not difficult to go there, but okay, you have to find your way. If you go along the street, you arrive at the tram stop. You can go from here and then cross here the street. You arrive at the restaurant. So what else? And okay, and the dinner will be on the boat, but it's not a moving boat. It's just a fixed restaurant. And finally, I would like to warn you, we have had some troubles in the university recently, so you should be aware that you don't. Okay, it's not. You should not leave your belongings unattended, because I'm afraid they will disappear very soon. So, and okay, so that's it for practical details. And now I will leave the word to Petro Mironescu, who is the head of this institution called l'ABEX Million, and who has been supporting us, especially financially. Okay, thanks.
Just introduce. So basically, what I'm going to tell is in the section our programs are going to resume after this announcement. The announcement. So hello everybody. I'm Petro Mironescu. I first thank the organizers for letting me present the Laboratoire Million. Was one of the main financial supports of this event. So Million stands for Mathématiques et Informatique à Lyon, Mathematics and Computer Science in Lyon. It is a new structure whose lifetime is about 10 years. His goals are to improve the Lyon's area attractiveness, and we have 3 lines of actions, which are research, training, and more specific to Lyon scientific radiation. And I will try to explain you that you have the opportunity to come back to Lyon. So one of our main activities is to support organization of thematic quarters and of international conferences. We started, I'm going just to present a few actions, it's going to be quite short. Few actions in the areas which are somehow related to Equa Diif. We started with a trimester in mathematical biology. This was a huge event, more than 400 participants for the trimester. And its main feature was that it brought together many people from outside mathematics. Half of the conferences were provided by non-mathematicians. This year events, you are here at Equa Diif. The conference of the Society of Industrial and Applied Mathematics just finished. Its main organizer was from our partner, from Spicami Jordan. And I want to advertise some forthcoming events. The first one is going to be a trimester in analysis. main organizer Isabelle Tati. And especially I'd like to advertise the conference in PDs in honor of Luigi Ambrosio in October, and in December, a winter school on nonlinear function spaces in mathematics and physical science. And next year, there are going to be 3 large events. One on high performance computing. This is going to be a huge event involving 12 research structures, and there are going to be 7 events, and a month on risks and climate change, and a month on geometric measure theory. And all the organizers are from the Institute of Mission. So this gives you good reasons to come back to you. Okay. Million is also different things, like the postdoctoral fellowships, invitation program, and very successful second-year master program, Mathematics in Action, which has almost 30 students for its second-year existence. And something which is specific to Lyon, where we take fun very seriously, which is the Maison de Mathématiques et de l'Informatique. And I know that this time you are going to visit the Musée de Confiance, but hopefully the next project is going to visit the Maison de Mathématiques, which is something we are very proud of, and many of the organizers are also very much involved, in particular, are also very much involved in trying to attract young students, high school students to mathematics. So I'm done. Welcome to Lyon, and I hope to see you back to the forthcoming. Thank you.
And now to complete this opening, we have the pleasure and honor to welcome our president, Professor Gilly, who will be saying a few words. Point.
Thank you, Sylvie. Well, ladies and gentlemen, dear colleagues, on behalf of Claude Bernard University, it's a real pleasure and honor to welcome all of you for this Equa Diif meeting in our university. I will say also welcome to the current French heat wave. I do hope that this heat wave will not be too unpleasant to you during this meeting. As far as Claude Bernard University is concerned, it's a rather large sciences, health, and technology university. It's more than 42,000 students. And Claude Bernard University is member of the Federal University of Lyon, which is a big structure with all the Lyon University. As Sylvie Benzoni told it to you, you are here on the Sciences campus, which name is Lyon Tech Ladois. Claude Bernard University has also other campuses in other parts of Lyon for health or for technology. Of course, inside Claude Bernard University, there are very large research institutes, and one of them, of course, is Camille Jordan Institute, which is our proudness, our mathematics research institutes. I would like to thank my colleague, Professor Sylvie Benzoni and Professor Thierry Gallet from Grenoble University for the organization of this meeting. I know that 5 of your young colleagues also participated to this organizing committee. I will thank also the Cellule de Congrès of our Claude Bernard University. I do hope you will have time enough to enjoy the city of Lyon. Probably it will not be the best weather to you due to the sunshine and to the heat wave, but I do hope you will enjoy our city. Once again, thank you to all of you for coming here. You are more than 500 participants coming from 47 countries all over the world. Thank you for coming, and thank you to Camille Jordan Institute for this nice organization of Equa Diif meeting. Thank you to all of you.
So we're going to continue on the scientific part. So now for our first chairman is Professor Mark Groth.
Yes, good morning, everybody. It's also a pleasure for me to welcome you to this Equa Diif conference. Let me begin by thanking the local organizers, Sylvie and TFE, and their young sisters, for agreeing to organize this conference. As the organizer of the previous Equa Diif conference in Loughborough, I know how much work it is. And indeed, the final task of the organizers of the Equa Diif conference is to select the location for the next Equa Diif conference. So I'd also like to congratulate the previous organizers on their wise decision of having this conference in Lyon. It's a pleasure to introduce the first speaker, who is Professor Andrew Stewart of the University of Warwick, where he's been professor since 1999. Professor Stewart completed his PhD in Bristol in 1983 and has been at a number of universities since then, including Oxford, MIT, and back in the UK, I'm glad to say, since 1999, as we already heard. His research interests are in the area of numerical analysis of dynamical systems, applications of stochastic differential equations, and data assimilation. And he's received several awards and prizes for his work. I'd just like to mention one or two: the LMS Julia Whitehead Prize, several awards from science, deep industrial and applied mathematics, and most recently an ESC Advanced grant. He's also been selected not just for his abilities as a mathematician, but as a speaker. And he's given several invited talks at other large conferences, notably the ICM in 2014, the EQIAM in 2007 in Zurich, where I indeed heard him. And I'm sure that today's talk will be of the same caliber. The title of this talk is Data Assimilation, New Challenges in Random and Stochastic Dynamical Systems. And in fact, he's the recent author of a new book on this subject. It's a subject of which I know very little, and I'm hoping to find out much more from this talk. Thank you.
Thanks. Sound good? I'd like to thank Mark for a nice introduction, and Thierry and Sylvie and all the other organisers for the meeting. I'm not going to say anything about the temperature. People in the UK spend the whole year complaining about the weather, and I'm not going to complain, and it's actually nice for once. Besides which, I have a fan up here, so the temperature is quite good for me. Okay, so I'm going to be talking, as Mark said, about data assimilation. This is an area in the broad area of stochastic dynamical systems, and it arises primarily from applications in geophysical sciences such as weather forecasting, oil prospecting, and so forth. But I'm going to concentrate on explaining to you the mathematical structure that underlies this subject, and hopefully stimulate you to become interested in the subject and see that there are many, many challenges here. I will scratch the surface in showing you some of the interesting mathematics that has been performed in this area, I believe. I believe it's interesting. And also try and show you that there are many open problems. So the work I'm going to describe is primarily work with Daniel Sansalonso, who is a PhD student at Warwick, but I'll touch on joint work with a number of other people whose names will come up as we go along. Okay, so I'll structure the talk with some introduction. I'll give you three take-home ideas around which the mathematics is organized. These are of interest in their own right, anyway, and each one of them individually is nice, and seeing the connection between them will give you an overarching view of how the subject works, how the mathematics of data assimilation works. I'll spend most of my time on discrete time problems, but these will come from differential equations. So the discrete time mapping underlying the mathematics, you should think of as a time h flow of a differential equation. And by the way, although I'm not French, I do know what equative means. It seems to have a clear meaning to me. So there will be differential equations underlying this, and then I'll go to continuous time and look at various stochastic partial differential equations that arise from taking limits in the discrete time picture. Okay, so this is the basic underlying setting, just to do the whole slide. So I'm going to talk about signal dynamics, which will be a deterministic dynamical system in a Hilbert space. Most of the time we'll just work with a single Hilbert space, but a little later in the talk there'll be two equivalent Hilbert spaces for reasons I'll make clear. We'll just have some deterministic map, psi. As I said, you should think of this as the time h flow of a differential equation. And I'm going to imagine that the initial condition is not known to us. So it's distributed according to a probability measure mu0. And in particular, you should think of problems where this comes from a chaotic dynamical system. So the uncertainty in the initial condition will make, as I'll come to in a moment, will make prediction very difficult. Just to specify things, and also because most of the applications that motivate this field come from dissipative physical phenomena, I'm going to assume the existence of an absorbing set. So I'm going to assume there's some compact set in the Hilbert space which absorbs all balls of finite radius in a finite time that depends on the radius of the initial condition. We then have a global attractor, which I'll call calligraphic A, and at the level that I've described the problem here, there's not much you can say in terms of predictability. What you can say is that the distance between the trajectory, now if I fix an initial condition rather than have it random, the distance between an individual trajectory and the global attractor tends to 0 as j tends to infinity. But the global attractor can be very complicated, and the amount of predictability within this statement is very limited. Okay. However, increasingly in many areas of science and engineering, we have data. And a perspective that I'd like to leave this talk with is that analyzing data and mathematical model together is a new paradigm for how we think about modeling and be very productive. So let me set up a situation in which we have both the signal process from the previous slide, but also data is available to us. And I will assume that the data is partial and noisy. So P is going to be a projection from Hilbert space where the signal dynamics lives into a finite dimensional space, Rj. And I'm going to assume that we observe data at each time, yj plus 1, which is the projection of bj plus 1 into this finite dimensional space, with the addition of noise. And I'll assume that the noise is centered, so it has been zeroed, and it is normalized so that its variance is epsilon squared. You should think of epsilon as small during this talk. And I will assume that psi later on will use the PDF that this random variable psi has, which I'll call rho. So in this situation, we've got randomness in the deterministic map through its initial condition, and we have randomness in the observation process. If we consider these two together, the natural object to study is the probability distribution carried by this signal given the observations. So the filter is the probability distribution of Bj given the observations up to time j, and that probability distribution, that time j, I will denote by muj, and muj of A is the probability that Bj is in A, given the sigma algebra of all of the data, the y's, up to time j. Okay. So this is a different dynamical system. On the previous slide, we had a deterministic dynamical system, possibly with random initial condition. And our interest is in V, which lies in the Hilbert space. I'm now focusing your attention on not on the signal itself, but on the probability distribution carried by the signal given the data. So muj is our object of interest. And the key point I want you to take away from this lecture is that whilst the underlying signal problem may be quite unpredictable, when you combine it with observations, there are situations in which the unpredictability can be controlled. So let me focus then on the dynamics that is undergone by the filtering distribution, the probability distribution on the signal given the data. So remember, Uj is this probability distribution of the signal given the sigma algebra of events, or all the data up to time j. So the dynamics of this signal process, the probability measure of the signal process conditioned on the data, can be described through two formulae. The first one is just push-forward dynamics. So you have the probability distribution at time j given the data at time j, and you push that forward under the map to get a new probability distribution, uj plus 1 hat, and then incorporate observations via Bayes' theorem. So this, you don't need to take in the data, the details of this formula, but there are a few aspects of it that I'd like to emphasize. So this second panel is a mapping from uj plus 1 hat to uj plus 1, and this is a nonlinear mapping. The first mapping here, push forward, is a linear map on measures, but this observation, the use of Bayes' theorem, is nonlinear because of the normalization constant. So this is a nonlinear map that takes uj plus 1 hat into uj plus 1. And just a couple of things in addition to that. The small parameter epsilon that describes the size of the noise is inside the formula. And rho is the PDF of the noise, which includes the observations. So, okay, this is a potentially complicated map now on probability measures rather than on the signal itself. However, what I will show you during the course of this talk is that this can be quite predictable. So although the underlying signal dynamics given by psi may be chaotic, given enough observations, there are situations in which, for small epsilon, this sequence of probability distributions converges to something that's approximately a Dirac measure centered on a particular signal which underlies the data as j goes to infinity. Okay, so I'm going to illustrate what I've just told you in slides now with a couple of movies. That means I wish I had 4 hands. I don't. I'm going to put down the microphone for a minute and just get the movies up. Excuse me. Okay, so the first movie I'm going to show is just an illustration of lack of predictability, and this shows at least one person in the audience will know it's not showing quite what I'm going to tell you it shows. But roughly speaking, what I'm going to show you now is the effect of uncertainty in the initial condition of the Lorentz equations and how that accumulates over time. So what you're going to see is the Lorentz equations as a system of 3 chaotic ordinary differential equations. You're going to see the PDF of each one of those components and how it evolves in time. So they're essentially start at a Dirac measure, which is why these are rather narrow. And as the uncertainty grows, you'll see that it starts to spread, and the PDF essentially spreads out over the entire attractor of the Lorentz equations. So this is highly unpredictable. We're able to predict that the Lorentz equations has a global attractor and that trajectories will asymptotically lie on it. But individual trajectories can do very different things, and the PDF that you see there are very spread out and characterize a great degree of unpredictability in the system. Okay, in contrast, I'm now going to show you, and the visualization here will be slightly different. I'm now going to show you what happens if we append observation of the first component of the Lorentz equations and essentially carry out the probabilistic picture that I described here. And here we're observing the red circle is the observed process. And what you see here is that there was initial uncertainty, which is characterized by the fact there's some spread in this, from what you see at the initial time t equals 0. But as time progresses, because we're observing this first component with noise, as you can see through these fluctuations, but by using that observation sensibly, in a way I'll describe to you in due course, we are able to predict what happens with this unpredictable, chaotic differential equation. However, it really matters what you observe, and this is something I'm going to get to in the course of the talk. It's not, I observed then one component of the Lorentz equations, and it's crucial that it was, in this case, the first component. I'm going to show you the same thing now where I observed the third component. And what you'll see is that initially, so the third component you see here, we're observing again with noise. Now this is not sufficient to make good predictions. As you can see, the trajectories that you're seeing here, the blue is the true trajectory that underlies the data, and our prediction is no longer accurate. They've moved an order 1 distance apart, and they will come together again in a moment, but that divergence between our prediction and the true signal is characteristic of this particular observation of the Lorentz equations. Okay, so those 3 videos demonstrated 2 things. I should say they demonstrated 3 things, otherwise there would be no point in having 3 of them. They demonstrated, firstly, the unpredictability of the Lorentz equations, and then they demonstrated that certain observations can be used to control that unpredictability, but thirdly, that it really matters which observations you use. Excuse me, I'll put this down. Okay, so let's look now a little bit into the mathematics of how we go about proving something like this. But let me just give you a little bit of history and give you a way of thinking about the mathematics that underlies the remainder of this talk. This is the idea of studying the predictability of deterministic dynamical systems in the presence of noisy observations. Was first studied in a paper of Seru, which appears in Science Journal of Control and Optimization in 2000. So the key question I want to address is this: for which dynamical system psi and which observation operators p does this filtering distribution uj concentrate on the true signal? This is what underlies the data, up to an error epsilon. That's the scale of the noise in the observations in the large time limit. And what makes this interesting is that, of course, we're not assuming that we observe the whole of the signal. So in the Lorentz equations I showed you, we just observed one of the 3 components. But what those examples showed is that an interaction between psi and p is crucial. So the key problem we're trying to overcome is the fact that psi may be an expanding map. Okay, that's what makes chaotic dynamical systems interesting. I'm going to be a bit schizophrenic in the way I view P. Sometimes I'll view it as a mapping from the Hilbert space H into a finite dimensional space Rj. Sometimes I'll just view it as a projection on H. It's mathematically convenient to be able to think of it either way. So here, if we think of P as just a projection on H and define Q to be I minus P, the key idea behind this talk is that the Q psi should contract. So this gives constraint on what we're allowed to observe, because Q is I minus P. P is what determines what we observe. And this is a very intuitive idea. The Q is, of course, the part of the signal that we don't observe, and the idea is that that should have some form of contraction. And there are many, I mean, this is just hand waving, but this is a basic idea which can be instantiated in many different ways, and I'll do that precisely as we go on. Okay, examples are also important. The theory applies more generally than this panel alone, but this panel will give 3 equations which are worth keeping in the back of your mind as examples of where the theory applies. So the 3 equations are the Lorentz 63 model that I've just shown you, the
three-dimensional system. Lorentz 96, which is a model widely used by atmospheric scientists of arbitrary but finite dimension, and the incompressible 2D Navier-Stokes equations with periodic boundary conditions. All of those can be written in this general form, where one has a dissipative linear term. So you have an inequality of this form, lambda positive, and energy conserving quadratic nonlinearity. So the inner product of B with V is just 0. And then F, mostly F will be independent of time, but you can also look at time-dependent Fs. So locally in time, it should be square integrable as a mapping into the orbit space H. Okay, so what I want to describe now is 3 ideas that are interesting in their own right. Many of you would have seen many of them before. And really what's interesting is how they fit together, but not all of you will have seen all of them before, so these ideas are interesting in their own right. So what I'm interested in showing is something about the accuracy of the filter, the ability, if you observe the right things, to reconstruct the signal in a chaotic dynamical system. And a key idea here, I'm going to work, as I said, within distributed systems. A key idea here is synchronization. And I'll give you some background on the particular flavor of synchronization that underlies this work. I'll then describe some ideas that originated in the weather prediction community that really kick-started this whole area of data assimilation, and a particular algorithm called 3D VAR, which is used by weather prediction centers around the world, and is also prototypical of more complicated algorithms that I'll come to later in the talk. And I'll link this to synchronization, and I'll show you how that works. And then a very simple idea from probability is the idea of the optimal filter, which is really an application of Galerkin orthogonality, which will enable us to use the 3D VAR as an upper bound on the filtering distribution that I focused your attention on a few slides ago. Okay, so synchronization. So this is an idea that has a long history. In the context of Navier-Stokes equation, we go back to a paper of Boyesh and Prodi in 1967, and then an important paper of Equa and Carroll, which looked at the Lorentz 63 model in 1990. And later I'll come to work that's come out of Boyesh and Prodi, much of it led by Idris Titi, which we will use on very specific examples. But here's the idea of synchronization. So on the left is the original dynamical system that I wrote down for V, split into its components projected by P, which is the observation operator, and Q, which is I minus the observation operator. So I've simply rewritten the original dynamical system by splitting into coordinates in the observed space and the unobserved space. So together, these two just give you the original dynamical system, and the dagger here I'm using to denote the truth, which will underlie data later on. The synchronization filter is based on what I call here the synchronization filter is based on the assumption that we observe the P component without any noise here. So we set the filter M is made up of P and Q. We just set the P component equal to the true signal, Pj plus 1 dagger, and then we feed that into the Q component of the problem. Okay, so we run the dynamics in the unobserved process, and in the observed part of the system, we just use the data. So that gives a non-autonomous dynamical system, which is driven by Pj dagger. That's the observation of the true signal. And you can rewrite that in this useful way. So the filter, the mapping from Mj to Mj plus 1 is given by projecting the dynamics in the Q direction and adding the data, which is in the observed component, to the P direction. Now, there are many situations in which it is possible to prove that Mj plus 1 converges to Vj plus 1 dagger as j goes to infinity. And this is synchronization. But by the way, this
talk I'll make available on my website later on, and you'll be able to follow up all of the references in detail. And I'll fill in some of these later on. But for many problems, you have the synchronization property that this filter, this mapping here, will converge to the true signal as j goes to infinity. Okay, so that's the idea of synchronization. Now I want to link that to 3D VAR, which is a methodology, as I said, used in the weather prediction community. And this goes back to a paper of Lorenz. Andrew Lorenz works at the UK Met Office. This paper appeared in 1986. And what I call here cycled 3D VAR is the following non-autonomous dynamical system. And I want to describe it to you as it's a cycled minimization. So if we just concentrate on the first panel here, I'm going to minimize something, and that something is a compromise between fitting the model, which is this quadratic term here in M, and fitting the data, which is this quadratic term here, which involves the data yj plus 1. So the first term says, given our estimate of the signal at time j, run that through the model, and we want one of the two terms in the minimization says we're going to try and choose M to keep it close to what happens when we take the estimate at time j and run it forward under the model. And that's going to be weighted in a way that I'll describe in a moment. But this is a weighted L2 norm, weighted Hilbert space norm. And then we also want to stay close to the data. So we also ask that PM, that's the projection of M into the observation space, is close to the data, yj plus 1. That's scaled by epsilon to the -2, recognizing the variance scale for the observations. And then what are these weighted norms? So these weighted norms are just the Hilbert space norm weighted by the operator c to the -1/2 in this case, and an operator gamma to the -1/2 in this second term here. So those operators characterize our knowledge of the covariant structure of the errors that we make in the model and the data. Okay, so they do matter, but the details don't matter very much. The key point I want you to grasp is that I'm going to minimize something which is a sum of squares, and the first term in the squares represents fit to the model, and the second term represents fit to the data. Okay, and you can solve this minimization problem, and that idea underlies what's known as the Kalman filter, which is the exact solution for the probability distribution I highlighted in the case of linear dynamical systems subject to additive Gaussian noise. But this is a generalization of that idea because here we have a nonlinear model. So psi is not necessarily linear, and for all the examples I gave, it is nonlinear. But if you solve this variational equation, and I'm going to do that with a particular choice of this weighting operator C here, and that weighting is chosen to depend both on the scale of the noise and the observation epsilon, and on the observation operator P and Q. And this is just calculate the Lagrange equations and look at them with this particular choice of C. What you get is the following non-autonomous dynamical system, which has a very intuitive interpretation. The 3D VAR filter, the sequence MJ, is comprised of what I would like to describe as an operator-convex combination of the model here and the data here. And the model and the data are weighted respectively by I minus K and K. And K you should think of as an operator which has norm less than 1. It may treat different components differently, but in that sense we have something here which is a positive and norm less than 1 operator. So think of this as a convex combination of the model and the data. And in fact, with this particular choice, K is known as the Kalman gain in the Kalman filter application, or just the gain. With this particular choice of C, K has the form that you see here. It's proportional to the observation operator, and indeed, as this parameter eta tends to 0, K becomes equal to the observation operator. And in fact, if you take eta equals 0, you recover from 3D VAR exactly the synchronization filter that I gave you on the previous slide. And so this method, which is, as I say, prototypical of methods used in the weather forecasting community, this method is very close to the synchronization filter. The synchronization filter had no uncertainty built into it. It concerned the situation where we observed without any noise the key projected signal. 3D VAR is concerned with observations which are polluted with noise. But other than that difference, if I take the limit eta goes to 0, the 3D VAR method is the same as the synchronization filter. So underlying all weather prediction methodologies, or so many sequential weather prediction methodologies, is the idea of synchronization. And indeed, taking eta very small, eta equals 0 gives the synchronization filter. Taking eta very small is known as variance inflation, and is something you'll see widely if you look in weather prediction journals. Okay, so here is demonstrating how that works. This is for the 2D Navier-Stokes equation, and I'm plotting here the output of the 3D cycled 3D VAR filter. This is the error as a function of time, which here grows to order 1 and saturates. And this is the difference between one of the Fourier components. I think it's the 1, 2 Fourier component in the wave number space. And the truth is in blue and the filter is in magenta, and they are an order 1 distance apart. So the parameter eta here is too large. If you decrease eta, then you get closer to synchronization, and you see that the error between the filter and the truth remains small. And if we look at this particular Fourier component that I showed on the previous slide, you see that is synchronized. The filter is synchronized with the data. Okay. So the third idea is filter optimality. So what I want to do in this talk is get a handle on the probability distribution that I call μj. And filter optimality is the statement that the mean of that filtering distribution, the average of the signal given to data under the measure μj, is optimal in the following sense. That if you take any mj, which is depends only on the data up to time j, so it's measurable with respect to the relevant sigma algebra, and look at the mean square difference between the filter and the truth. This should have a dagger on it. This is what I've been calling BJ dagger earlier. The mean square difference between any measurable function of the data and the truth always exceeds the mean square distance from the mean of this filtering distribution. So that means we can get bounds on the filtering distribution by, which is on the left-hand side, by bounding the right-hand side. And what I'm going to do is to use the 3D VAR filter, with a variant on it, to bound the right-hand side, and that will give a bound on the left-hand side. And although I'm not showing it here, you also get bounds on the variance of the filter in the same way, and that gives you concentration of the filtering distribution close to a Dirac on the true distribution. Okay, so let me show you how that theory works, and let me give you the setting in which we will undertake that theory. So the dynamical system I wrote down is set in a Hilbert space. To apply the theory I want to apply, I'm going to introduce a second Hilbert space, V, and these are equivalent. Just a note to those of you who work in the Navier-Stokes field, for which this is an example. H is not L2 and V is not H1. These will both be H1, divergence-free H1 spaces in the Navier-Stokes example. Okay, so these are two equivalent Hilbert spaces, and two assumptions that I'm going to work with. firstly, the existence of an absorbing ball. So I described this to you at the very beginning of the talk. So there's a ball of radius r0 with the property that if you map that ball forward under the dynamical system, you map into the ball itself. So it's in forward invariant. And secondly, that any bounded set is mapped inside this ball of radius r0 in a finite time. So if you take any bounded set in the Hilbert space, then there is a time j which depends on that bounded set, such that if you iterate the dynamical system j times, you're inside that ball of radius r0 after j steps. And then you will remain there by the previous bullet. Okay, so that's the absorbing ball property. And if additionally you have some compactness, then this gives you a global attractor. Then the squeezing property, and here I'm deliberately using terminology that you will find in the inertial manifold literature from a couple of decades ago. This is very, very similar to what you see in that field. The squeezing property is the statement that we have a contraction, not of psi, because that may be a chaotic dynamical system, but of q psi. So specifically, for any pair UV, which are in this absorbing ball, we have the property that the distance between q psi applied to U and q psi applied to V squared is strictly less than the distance of U from V. And just what makes this slightly technically interesting is that to carry this out, you'll notice that this ball is in the original Hilbert space H, whilst the squeezing property may be in the different but equivalent Hilbert space V. And we'll need that for some of the examples. Then under those two assumptions, we essentially have the thing I really wanted to achieve, which was a concentration of the filtering on the truth. So this Vj is what I called Vj dagger earlier. This is the truth. And this is the mean of the filtering distribution. So this is the mean of the signal under the measure Uj, which is conditional on the data up to time j. So this says the mean of that distribution does not deviate in the large time asymptotic very far from the truth. And you can also use this to get estimates on the variance. So this is essentially proves the concentration of the measure near to the truth, and it means that we have predictability. So under the two preceding assumptions, I'll show them again, we have a dissipativity property, and we don't have a contraction, but we have a contraction in the unobserved part of the dynamics. Under those conditions, we can control the error asymptotically, and the variance is of the same size as the variance in the observation. So this is interesting because we are accurately predicting a dynamical system which is chaotic based on only observing part of it. Okay, so the idea of the proof is to take the 3D VAR method that I described to you previously. That will be this algorithm here without the calligraphic P. So without the calligraphic P, this is the cycled 3D VAR in the synchronization limit where eta tends to 0. And I'm also going to add to it a projection in the space H into the absorbing ball. Okay, that looks like quite a big change to make, but because the dynamical system is such that there is an absorbing set, one can show that with high probability this projection is not used very often as you cycle this through J. So essentially this behaves like the 3D VAR algorithm with very occasional projections back inside the absorbing set, and they control outliers in the data. So occasionally the data can produce observations which are not really consistent with the dynamics, and this overcomes that. Then what I'm going to show you is a simple proof will show that the distance between this filter and the truth in the large J asymptotic is of size epsilon squared. So in other words, we transfer the observational noise to the noise, to the size of the observational noise determines the asymptotic size of our error in prediction. And then once I've estimated the 3D VAR, I can use the Galerkin property or the optimality of the filtering distribution to get the original result up here. Okay, so let me show you the proof, and I'll just sketch the idea. Really very straightforward. And I'm going to ignore the projection back into the absorbing ball. As I said, that matters only with very low probability. So let's ignore it just to see the ideas. This is the filter. There's the data yj plus 1. And the data is the projection of the true signal plus small noise. And this is the running the model forward in the unobserved component. The true signal itself is just Vj plus 1 is psi of Vj. I can split psi of Vj into the unobserved and the observed spaces. So I've got Q psi of Vj plus P psi of Vj. They add to give psi of Vj. And I write it this way because you then see the cancellation between the contribution of P psi in the true signal and the contribution of P psi which appears in the data. And if you now take account of that cancellation, subtract these and control the error, then a very straightforward calculation using the independence of the noise shows you that the error, the mean square error at time j plus 1 is less than or equal to the number alpha, less than 1, times the mean square error at time j, plus order epsilon squared. And then you just apply the global limit. So really very straightforward proof technique. Okay, and these ideas apply to the three examples I gave you at the beginning, the two Lorentz models and the Navier-Stokes equation. So let me just take you through those examples. And I want to highlight that for the Lorentz 63 and Navier-Stokes model, our analysis is very much built on a really nice paper of Hayden, Olsen, and Titti, which appeared in Physica D in 2011, which looked at what I call the synchronization filter, the noiseless case, right at the beginning. And that paper studied the Navier-Stokes equation and used Lorentz 63 as an example. And I would call your attention to that paper. It's a very nice paper which makes the translation from squeezing property and the work that built on Foyash and Prodi in the 60s and shows its relevance in data assimilation. So Lorentz 63, I've written it here in terms of, I've written it grouping the terms together abstractly to show you how it fits into the simple example, the general example framework I had at the beginning. The observation matrix P, here just observing the first component. And then the theory is applicable with the original Hilbert norm being just the Euclidean norm, that's this one here. And the second equivalent space with the double bar is just equivalent to the Euclidean norm, but we double weight the component that is observed. Okay, so we add to the Euclidean norm an additional term, which is the projection of the signal into the observed component. So that double weights that in the Euclidean norm. Then you can apply the preceding theory. Same thing applies to the Lorentz 96 paper, which was actually published in 2000, but came from a talk which Lorentz gave in maybe in 95 or 96. Same idea here, and the same choice of the second norm. And the observation operator here, for which the theory works, is an observation of 2 out of every 3 points in this dynamical system of size 3j. So observe 2/3 of the points. And then one can look at the Navier-Stokes, 2D Navier-Stokes equation in a periodic geometry. So this is really the key result in this paper of Hayden, Olsen, and Titti, which underlies our analysis. One can prove synchronization provided one observes enough Fourier components. So the observation operator here is defined in Fourier space. So here's an expansion of the velocity field in divergence-free Fourier basis, and the observation operator is to observe with wave numbers less than Kmax. If Kmax is large enough, and if you the h is the time step between observations. If that's sufficiently small, then using this theory of hadron symmetry and combining it with building it into the theory I've described, one can prove that one has synchronization for the Navier-Stokes equation, which of course can be chaotic, and that's included in the analysis. So just to summarize, for these three models, we have dynamical systems of dimension 3, 3J, and infinity. They're chaotic, but we're able to make predictions about them by making observations of dimension 1, 2J, and finite, respectively. So this really is the key idea. If you look at data and model together, you may have predictability. Of course, that relies on some analysis, and what I've been talking about is the relationship between what you observe and the underlying dynamical system, and coming up with some conditions which are sufficient for predictability with observations. But I emphasize those conditions are sufficient, and there's much room for innovation in generalizing these results. Much need for it as well in terms of application, because the kind of, for example, the size of Kmax that's needed here in the turbulent regime would be way prohibitive to make theories of this type work for geophysical turbulent systems in weather forecasting. So this is the beginning of a theory, and there's certainly need for these ideas to be extended substantially. Okay, in the last 6 minutes, is that correct, Mark? Or Mark? 6 minutes, okay, thank you. In the last 6 minutes, I'd like to talk a little bit about, well, going to continuous time, and also introducing a second idea, which is the idea of the ensemble Kalman filter. Both of these are interesting. The ensemble Kalman filter leads to networked coupled dynamical systems, and those are interesting. I want to explain how those come about and to highlight the fact that there's a real need for mathematicians to analyze these problems. And secondly, I want to describe the continuous time limits, because here we'll get some interesting stochastic PDEs. And I think for many of us, although the data doesn't come in continuous time, we can understand structurally what's happening in a lot more clear fashion by looking at continuous time. So let me start by telling you about the ensemble Kalman filter. And it's a very simple idea if you express it right, and it's a horribly complicated idea with indices all over the place if you look at the wrong papers. But this is the minimization principle that I described before for 3D bar, with the exception that rather than having one minimization principle, I have capital N of them. So this is the ensemble. Rather than making one prediction, I'm going to make N predictions. And the key idea of the ensemble Kalman filter is that the weight, so remember there were weights on this quadratic minimization. There was a covariance weighting the belief in the model and a covariance weighting the belief in the data. So the covariance in the model is Cj, covariance in the data gamma. The idea of the ensemble Kalman filter is to run n copies of this minimization principle cycled in time j. So n is indexing the number of copies, j is still time, and to compute the covariance empirically from those n ensemble members. So that's this panel here. So you compute the mean of the ensemble members, and then the empirical mean, and then you compute the empirical covariance. So this is the outer product, or the, if you like, this finite dimensions, the second term, the transpose. So this is the empirical covariance, and that couples together these n. So these minimization principles, there's n of them, but they're coupled together through Cj. And also for reasons that I don't want to get into here, but which are good reasons, several of them, it's commonplace to perturb the data. So you take the original data, and for each n, you add a small noise to that data. I'm happy to explain that to anyone who's interested afterwards, but it's not key to this, what I want to get across here. Okay, so that was one idea different from the generalization of the 3D bar we looked at before. But you really see this begins to be very interesting, because we're now coupling together a whole load of dynamical systems through this covariance. So if I go to 3D bar first of all and take the continuous time limit, what do we get? We get something, so think of the Navier-Stokes equation as a canonical example. So this is the dissipative term, and this is the convective nonlinearity, and that would be the forcing. And what we have in addition is something that looks like you've got the damping, which forces the filter M to go back towards the signal V. So this should be V dagger, if this is the true signal. And you've got noise. So it's like a damped-driven Navier-Stokes equation. And the damping is only in the observation space. So the challenge here, if you now return to my original question of asking whether we synchronize or whether M becomes close to V, is to ask whether there's enough damping in the system, whether we observe enough to overcome the instability in this part of the system. And one can carry out the same kind of analysis that I did in discrete time for this stochastic PDE, and that was in the paper with that I mentioned here with Lonka and others. In the case of the ensemble Kalman filter, you get, there are various different versions, but one gets systems of coupled Navier-Stokes equations. So each Vn solves a damped-driven Navier-Stokes equation, but the damping and the driving involve this covariance matrix C, which couples together all of these different damped-driven Navier-Stokes equations. So really quite an interesting structure here. You have standard dissipation, quadratic nonlinearity. You have Brownian motion in time with some covariant structure in space. This is small, and then but it's all coupled together through the other members of the ensemble. So these are really quite nice, interesting, difficult dynamical systems to study. I'm about to finish, and we're really crying out for more mathematicians to get into this field and deliver results about them. I'll just highlight two. So as I mentioned, in the 3D VAR case, one can prove results analogous to those that I described in discrete time. And in recent work with David Kelly, we proved well-closedness of those coupled Navier-Stokes equations damp-driven through an empirical covariance. And there's some interesting recent work that generalizes both of these, also involving at least Titi and co-workers for the 3D VAR, showing how one can incorporate pointwise observations rather than Fourier mode observations, and some more recent work of Tom Mider and Kelly, same David Kelly, who's speaking in the session tomorrow on inverse problems, which proves ergodicity of these coupled ensembles. Okay, I will cut to the end. As I said, I will put this on my website for those of you who want to follow up the references in detail. The basic conclusion is thinking about the model and the data together is a new paradigm for how we do mathematics, driven by the fact that data is everywhere. And it leads to new interesting mathematical problems. In the context where the data is time dependent and we have some sequential way in which the data comes to us, that field is called data assimilation. You'll find many of the references if you look online to this talk. And I did want to just mention this book, which is a textbook that summarizes the area with Cody Law and Kostas Zigalakis that will be available later this year. And in any case, you can download half of it for free from my website, and along with MATLAB files, which can be used to reproduce the figures in there and play around with. And of course, most importantly, all of the references to other people's work are in here. I had a massive battle with both Springer to allow us to put half of the book on the web, and then a massive battle with the archive to allow me to put this book on the archive. I won both of those battles, and you can also find half of the book on the archive. Okay, thank you very much.
Thank you very much, Andrew, for this very nice talk. Is it the same half of the book on your website or on the other? The organizers have asked me to be strict with questions because the room isn't so suitable for that. So I decided unilaterally to be very strict with questions. And instead of inviting questions from the audience now, I'm going to invite you all for coffee downstairs and ask Andrew to make himself available for questions there. Once again, thank you very much for this talk.
seul. Oui.
It might be terrible idea.
Comme ça, les maisons se doublent à chaque fois, puis on a un grand orage.
Moi, j'ai pris un aspirateur industriel comme de chantier. J'ai l'idée ensuite de faire ouais,
J'aurais tout donné dedans et je prends tout le chaud.
C'est ça. Parce qu'en fait, du coup, il n'aime pas du tout les dire. Ouais, mais et vraiment, il a eu des soucis de caméra, il a mis son portable en webcam. Je crois pas qu'il puisse tellement. Ah oui, d'accord. Parce que son système ne fonctionnait pas. Du coup, il a juste mis son. Je sais pas s'il a encore là. Je crois pas qu'il peut en faire une. D'accord. Donc, si on peut faire une. Dans ce cas-là, si on peut faire une vidéo, c'est. Oui, je vais tomber sur le. Je vais essayer de voir si. Je vais demander aux hommes.
Non, c'est ça, une machine qui va retransmettre ce qui est en temps réel. Voilà, c'est 0,1. Effectivement, moi, je vais
Voilà, ça que je veux dire, je vais aller voir avec
s'il y a un PDF, après.
il y a un PDF.
Oui, mais sur format, oui.
Ah bon? Et sinon, est-ce qu'on peut brancher non, on n'entendra pas, on aura plus de mal à synchroniser.
Pour choper le son,
Ouais. Et il n'est pas du tout dans les parages.
après, oui, j'ai retourné à Ica pendant une vie.
C'est-à-dire que le système a planté et
Tout ce fait, il avait trois.
il n'est pas là pour nous aider. D'accord.
Je vais voir si j'ai plus vidéo.
Bon.
En effet, là, la situation n'est pas bien compliquée.
Si le webcam est ouvert, le son. Oui, mais le but, c'est que l'image, on ne remet pas l'image de la webcam.
Que le PDF. Oui, c'est ça, moi, les webcams, c'est pas mon truc, mais effectivement, il faut que.
Là, j'ai aucune idée de.
Ah, j'ai fait ça déjà.
Il est branché comment?
Oui, bah, c'est comme ça, d'accord. Lui, il est branché à rien du tout en fait. Il filme avec sa webcam et avec le micro de son ordinateur. Et par contre, comment est-ce qu'il transmet?
Voilà. C'est possible de l'avoir en téléphone.
Bah, je vais essayer de choper.
Ouais.
Oui, ça va être ah, d'accord. De la technique, on est sur la question. En fait.
On essaie de résoudre.
Ouais, on essaie de trouver une solution qui permet de voir les là-bas, sur le film, ça marche pas.
Et là-bas, il y a un ordinateur auquel on peut relier. Ouais, non, déjà essayer de mettre
déjà, on passe avec PDF dessus et le faire lire, et voir ce qui passe et mettre le.
Oui, mais il faudrait qu'ils entendent le son. Quoi,
juste le PDF.
Est-ce que c'est possible de l'avoir au téléphone?
Je vais.
Alors, déjà, ça fait. Demain, copier ce dossier.
Oui, bon, on va le faire de toute façon. Hein.
On va essayer. Et on peut avoir quand même le son de...
Là, on va tester. Il n'y a qu'une seule manière de le savoir, c'est d'essayer. On va garder la webcam dans au fond, on va mettre le sac dessus.
Du coup, on me voit bien.
Parce que j'arrive pas à joindre.
Hop. Alors, déjà, on va essayer ça. Et je vais aller voir ce qui se passe.
Test. Test webcam. Test micro webcam. Test micro webcam. Amphi à 13. Test micro webcam. Amphi à 13. Voiture à webcam.
Alors, est-ce qu'on peut gérer ça? Là, bon, je peux rester à côté pour les bouger en temps réel comme il faut.
Pour l'instant, la webcam garde le dessus. Hein. Et si on la réduit,
je vais voir. Je pense pas. On a dit avec déjà.
Sinon, ce qu'on peut faire, sinon il y a une autre option, il va falloir tirer du câble. On part du multiplaire, on tire 20 mètres de câble audio, multiperson. On tire 20 mètres de câble audio jusque dans la salle, je pense que c'est accessible.
Et ça, c'est pas faisable en parallèle. Là, ça commence en 10 secondes.
Bah, il faudra.
On peut au moins régler un zoom peut-être pour essayer de voir. On arrive à voir les efforts.
Il faut que je retrouve la webcam.
On va brancher comment ça? Ah oui, on va perdre le son sur étiquette, tout simplement.
Ce qu'il y a.
Ok, donc c'est un grand plaisir d'introduire Sylvia Sarfati, l'Université Pierre-Marie Curie. Donc Sylvia is a professor not only at the University Pierre-Marie Curie, but she's also a global distinguished professor at the Courant Institute. And since 2014, she is a member of the Institut Universitaire de France. She has received many prizes. I'm going to mention just a few of them. In particular, she got the NSF Career Award, the European Math Society Prize, the 2007 European Young Investigator Award. In 2012, she was a plenary speaker at the European Congress of Mathematics. And also in 2012, she got the Henri Poincaré Prize from the International Institute of Math Physics. And finally, in 2013, the Grand Prix Murphy de l'Académie des Sciences. Okay, so without further notice, she will be speaking on effective models for Ginsburg.
Thank you very much, Julia, for this introduction, and thank you to all the organizers for inviting me and for putting together this conference. And thanks to all for coming in spite of the weather conditions in the room. So I would like to talk about effective models for Coulomb vortices, starting from a short story and moving to some more recent story. The outline would be that I will start by presenting regarding the Ginsburg model and the situations that go with it, in particular the situation with the fixed bound number of vortices, the limits of minimizers, critical points, dynamics. Then I will move to the gauge Ginsburg, similar results that were obtained moving to situations with unbounded number of vortices. And finally, dynamics for large number of vortices. Okay, so what are we looking at? We're looking at the Ginsburg equation, the Ginsburg model. It's an equation for complex value function U, and typically I will think about two dimensions. I will mention a few words about higher dimension. The domain, let's say, in R2 into the complex domain U, and so this is the Ginsburg equation with the parameter epsilon, which later is multiplied to 0. There is a two time-dependent equations that are associated with the parabolic version, parabolic Ginsburg equation, which is PTU in front, nonlinear heat equation, and a Schrödinger version with IDTU in front, which is, of course, a particular instance of NLS, of nonlinear Schrödinger, but with this particular nonlinearity, it's usually called the Ross-Beta-ST equation. All these equations are variational, that there is an associated energy, which is this one. Okay, and so these equations can be considered as one of the relatively fundamental models of mathematical physics. In particular, they are crucial for the modeling of superconductivity, superfluidity, Bose-Einstein condensates, and have some connection with nonlinear optics. All right, so the thing we're interested in is the vortices. So in general, you can observe that by maximum principle, the modulus of the complex value function U is going to be less than 1, and physically, the modulus of U represents the density of superconductivity or superfluidity. So it's like a phase field model. So where mod U is close to 1, it's the regions in the plane where your sample is superconducting or superfluid. And where modulus of U is close to 0 is the regions where it's normal, where you have lots of superconductivity or superfluidity. And in fact, they often are associated to true zeros of the complex value function. And those zeros with non-zero degrees, we call them vortices. So you have to remember that U is complex value. So whenever U vanishes around the 0, you can have a non-zero topological number, which means that U can make a turn of the unit circle around 1 and 0. So if you want to look at it in trigonometric form, you write u as rho to the ei phi, and the vortex of u will correspond to a place where rho vanishes. And the degree would correspond to the winding number of the phase. So it would be written like this. If you look at the small circle around the 0 of rho, and you compute 1 over 2 pi, the tangential derivative of the phase, of course, is going to be an integer, and that's what is called the degree. Okay. So the pictures you find in physics textbooks are of this form. You see rho, the modulus of u, vanishes somewhere, and then it goes back up to being close to 1. And H here on the picture represents the induced field that's created around the vortex. So vortices, they come with a natural length here, which is the epsilon in the equation, in the model. So that's their core size. And usually one says that they have a core and a tail. So the core is the region where modulus of u drops from 1 to 0. And the tail is the sort of big annulus around that region where the vortex still carries a lot of energy. So it's really like vortices in fluids, if you want to understand it in a simple-minded fashion. And so in the limit when epsilon goes to 0, this core size of the vortices becomes 0. And the vortices can be seen as points, so there will be limiting points. And of course, if you're in dimension 3, instead of points, you would have lines, curves, and vortices. And if you're in higher dimension, you have codimensional objects. Okay, so the main goal of this lecture is to describe effective models where you start from the complete PDE and you reduce to a simpler model, just telling you what the vortices do, where they are, how they move, etc. So it's an effective model for the vortices, like a reduced one. Okay, so the story starts back from the 90s with the work of Equa, who studied the minimization of the energy E epsilon associated with the Gibbs-Bourlangeau equation. So if you want, it's minimizing solutions to the equation. When the number of vortices is a priori prescribed to be n, and it's prescribed by some, let's say, by some boundary conditions, fixed Dirichlet boundary condition. What they saw is that the minimal energy scales like pi n log epsilon plus the minimum of a certain function w plus little o. Okay, so the pi n log epsilon here corresponds to the energy contribution of each vortex. Each vortex, due to its tail extension in space, carries an energy that's pi log epsilon, at least. So if you have n vortices, you're going to have at least pi n log epsilon. Of course, it's growing up as epsilon goes to 0. But if you go to next order, you see something which is not growing up and which is a more than 1. And which is this function w that's written here. So what they show is that if you start from minimizers of the energy, they will all have vortices that are of degree plus 1. So it will be all degree minus 1, but up to a change of orientation, which is reduced to the situation of degree plus 1. And their vortices will tend to minimizers of this energy function. So an energy function of this one. So what is this energy function? It's a sum of pairwise logarithmic interaction between the vortices weighted by the degrees. So here it's plus 1 or minus 1. In general, it's the degrees that are here, this integer. And there is some terms that are related to the interaction with the boundary as around this way. So basically, this is telling you that vortices interact. They interact in a logarithmic fashion, or in a Coulomb fashion. In fact, they repel each other. So if vortices have same sign, they repel each other logarithmically. If they have opposite sign, they attract each other logarithmically. And this is really the underlying effective model, if you want. And then you just have to minimize this interaction subject to whatever boundary conditions you want to do. It's called renormalized energy.